Hello, Gen Chem students. Let's continue talking about weak acids and weak bases, and we are going to focus on weak acids in this discussion. So go back to our notes. We had already talked about how to compare the strengths of the acid based on their structure, the number of oxygens and things like that. But pretty much I am now talking about everything but the big six. Everything but the big six has to be written in equilibrium. Well, turn that back on. So we need to be able to come up with those calculations using the equilibrium numbers so that we can find the pH of a weak acid at equilibrium. All right, well, what are our weak acids? Again, anything but the six, but if we wanted to, we could characterize them as molecules containing an ionizable hydrogen, in case we're comfortable with those. That means HA, just as a generic weak acid. But we're also going to consider the cations. Oh, what kind of cations? Cations other than the ones that come from the strong. I know that doesn't make much sense right now. I will show you in just a minute. So we have to go back to the definition of what an acid is. An acid is a proton donor. So any equation that gives us a proton in the product would be considered an acid. So let me go over to the whiteboard and look at both of these examples. All right. And we're pretty comfortable with the ionizable hydrogen. But it's all about the equation. So Ha makes a proton an A minus, and here's the key. It's considered acidic if it donates a proton or it makes a proton on the product side. So let's take a look at a cation. All right, let's just take, for instance, zinc. Now the key here is this is also reacting with water. So I'm going to write the water a little bit differently. And it's going to take two of those. And we're going to make zinc hydroxide and two protons. Because the zinc hydroxide is weak, and so it will come out as a solid, and it will force the equilibrium, if you will, to go to the product side. And I don't know how many, I'd have to find the K value, but guess what? It also created protons. So therefore, the cations are also considered acidic when you place them in water. Now, I mentioned something about except those ones that come from strongy. So the except is the cations in the strong bases. So we've got potassium, lithium, sodium, calcium, barium, and strontium. Okay. Again, there's nothing special about it, but we are going to trust the equation. So let's just take sodium, for instance. All right, sodium, my question is, will you react with water? And if it did, it would make sodium hydroxide. All right, that's what could happen. But I need to know, will it happen? And the answer is a big old no. Because, take a look at this first. Number one, all sodiums are soluble, so you are not going to make a solid. And it's 100% soluble, so that means really that's what you made. Well, if sodium never combines with the hydroxide in the first place, why would it have left the proton in the first place? So let's remember our rule. Nature loves neutral, and the lowest energy, and we get to add one thing in there, and the weakest acid. All right, so let's take a look at this should have happened in the first place. Sodium hydroxide is a strong. So the minute I started to create a stronger base than something I started with, the answer is no. So that will happen every time we use one of these cations that go with what? The strong bases. So all cations are considered acidic except those that are attached to the strong bases. All right, so we've got our ionizable hydrogens, and then we've got our cations other than those few. All right, and we come up with the equilibrium expressions. All right, just like before, if we have a equilibrium equation, K is to the products over the reactants. And then we have to ask ourselves, can we find this K value somewhere? And if this is an ionization equation, we could say yes. If it's at room temperature, I can look up that K value. And so there's my first two steps done. But how are we going to use that data in the calculations? And so that's what we're going to do right now. And I do need to show you one other little nifty trick. So the pKa, remember the P just stands for I took the negative log of it. So we have been comparing equilibrium constants. Hey, does it favor products? Does it favor reactants? Well, I want to compare acid strength based on the Kas. So I'm going to jump over to the whiteboard again. And this is a nifty little trick. The pKa is the negative log of the Ka. This is not pH. Okay, this is literally the negative log of the Ka. But sometimes it's a nicer number, one of those bigger numbers, so that we can compare them. So for acetic acid, the Ka is 1.8 times 10 to the minus fifth. If I take the negative log of that, the pKa is 4.74. So if I was to say, hey, what is the strength of this acid? We could either go back to the K values and say, oh, that's less than 1, so obviously it's not favorable. And I'm just making this number up. Ka is 1.5 times 10 to the minus sixth. If I was to compare these two, well, a negative sixth, that favors reactants a lot more. So this one is a weaker acid. Or I could do the pKa, and the negative log of that, touch my calculator, is 5.82. And then just like with pHs, it seems a little backwards, but the larger the pKa, the weaker the acid. So instead of trying to compare those two tiny numbers, I can compare these nicer numbers, and this one is obviously larger. So it is the weaker acid of those two. So that's a nifty little tool that we can use that negative log value for something else. All right, so the larger the pKa, the weaker the acid. And now let's do those calculations. We are literally going to plug them into our ice tables. So We're going to start with only the monoproducts. They only have one hydrogen that could ionize. And then we're going to have to do some simplifications if we want to get rid of that nifty, having to plug into the quadratic. And so we could just do the quadratic, of course, which is fine. Or we could do something called successive approximations or the assumption. Okay, so successive approximations and or we can assume that it ionizes less than 5%. All right. And then I also have to worry about, well, doesn't water make protons all by itself? Don't I have to consider that it's adding protons into my solution? And the answer is yes. And the easiest way to do this is to just go through an example for you. And so we're going to do vinegar. All right, vinegar, step number 1. We need a balanced chemical equation. Step number 2, come up with an equilibrium expression. Step number 3, can we find that K value? Yes, we can. So on the orange pages, so the Ka is 1.8 times 10 to the minus fifth. And then as part of the problem, I have to tell you something. So in this particular problem, we have 10 mils of 0.10 molar. Okay, so I'm telling you that that was part of the problem. Okay, now I have to fill out my ice table. And so, do you know the concentration of your beginning acetic acid? And the answer is yes. Now, just a quick note. Do I care that there's 10 milliliters right now? If I haven't combined anything to it, the answer is no. I could have 10 milliliters, I could have 100 milliliters. The pH is going to be the same as long as I haven't combined anything. So right now, the 10 mils isn't important. I just care about the 0.10 molar. Did I put anything in there with my vinegar? No. So the initial concentrations of those are 0. And how is it going to change? Negative x plus x and x. So equilibrium is 0.10 minus x, x, and x. And I didn't give you any equilibrium numbers, so there is your ice table. So can I plug those in? Well, technically they are the equilibrium concentrations. So 1.8 times 10 to the minus fifth is equal to x times x over 0.10 minus x. All right, here is the first assumption. Okay, I could go on and I could do the quadratic. Yes, but here's my first assumption. If this is a weak acid, then x should be very small. If x is very small, it's not going to change the number and it's not going to change the math. Okay, now that's an assumption. I can assume that, but I better check it in the end. And it's going to work as long as it ionizes less than or equal to 5%, which means 95% is still in the acetic acid form, and only 5% of it has actually gone on. Okay, well, let's try it. So you may ignore any plus or minus x. Okay, so I can't ignore the top x's, but this one right here, because I'm subtracting it from a quantity, I'm going to assume that's so small that it's not going to affect my quantity, and so I'm going to get rid of it. And so I'm now going to calculate that out. So 1.8 times 10 to the minus fifth times 0.10 is equal to x squared. So x is equal to the square root of, plug and chug, 0.8, negative fifth, 0.1, 1, 2, 3, 4, 5, 6. So 1.8 times 10 to the minus 6. So x is equal to 1.3 times 10 to the minus third. All right, great. What in the world did I just solve for? I literally found the value of x. Well, what is x? X is how much ionizes. Well, if my assumption is going to be correct, that better be less than 5%. Well, how do you find a percent? You take what you're interested in divided by your original. So my original concentration was 0.10. Convert it into a percent. And I'm left with 1.3%. So what it is telling me is only 1.3% of the acetic acid at 0.1 molar actually ionized. So what would that make it? 98.7. So 98.7% is right here. And only 1.3% has ionized, which is definitely a weak acid because it's still in its original form. It did not ionize. And that falls within my 5% rule. And I like to put a little note next to it. So that's less than or equal to 5%. So, okay. Okay. So it was obviously valid, and I can go on and I can check. But I need to prove that to you. All right, there's two ways I can prove that to you. I could go through and do the quadratic. All right? Yeah, no, let's not do that. Let's actually subtract that number from my original and see what I get. Let's see, so 0.10 molar minus 0. What was it? 0.0013. And if I subtract those to our significant figures, we only get to keep 2 after the decimal. So 0.1 minus 0.1213, and I get 0.0987. And guess what? This would round up. So it is so small that it did not change that value at all. In another example, I'm going to show you that that will fail, and then you can choose between successive approximations and going back to the quadratic. But this one looks great. This one looks great. So I now have my value of x. So I can now say my equilibrium values are, guess what? Pretty much still 0.1 molar over there. And 1.3 times 10 to the minus third molar. Don't forget your unit. And 1.3 times 10 to the minus third molar there. Now, if I want to convert that to a pH, I would need to take the negative log of the equilibrium concentration of the proton. So if I want the pH, it would be the negative log of 1.3 times 10 to the minus 3. And that is 1.3, 3, 2.89. And remember, there's 2 total, so you get 2 after. So this pH is 2.89. Did we expect an acidic pH? Yes, we did. All right, so that's how you would go through and you would do the assumption, okay? You do the assumption. So right here, we just did that. It may be ignored if it's small enough that it does not affect, and our cutoff line is 5%. We're not going to check that by quadratic or successive approximations, but there will be a practice problem coming up that I will check it for you. All right, the next thing I need to worry about is this water thing. Because water all by itself will do this. Well, guess what? That's an acid. So water by itself already has some protons. So if I add my weak acids onto that, when should I ignore that water is actually significant? And remember, 1 times 10 to the minus seventh is water at equilibrium. So as long as the number from the weak acid, okay, so as long as this number is greater than or equal to, we're just going to say the magnitude 10 to the minus sixth, it is okay if we ignore water. So go back to our problem. And this magnitude is clear up in the -3. So it is greater than or equal to 10 to the -6. So it is okay to ignore that water actually ionizes. And yes, there are points associated for showing me that you have done that. Okay, so make sure if you use the assumption that you've checked it and that you've also checked that you may ignore the ionization of water. And hopefully that becomes second hat as we do some calculations. Okay, let's try one more. And guess what? I have some down here for you. Just a note before we go on, everything that we have been using is called monoprotic. And so if you look at your reference sheet, monoprotics only have one Ka value. If there is more than one proton that can ionize, those are called polyprotic, and then you would be given successive Ka values. Okay, and we'll play with those in just a minute, but all the calculations we're going to do right now is for monoprotic. So we'll talk about those right here, but I give you a whole bunch of practice problems, and we are going to work through those now. All right, in a nutshell, weak acids, they can be the ionizables, or they can be the cations that don't come from the strongies, and you have to do the equilibrium, and you may use those assumptions. And so I will do the problems in a different video so it's shorter. All right, until next time, jolly out.